Now we have the question of whether V1 equals 1, 0, 0, V2 equals 1, 0, 1, V3 equals 1, 1, 1, span R3. Well, three vectors span R3, but definition is very similar to what you have here. The set of vectors span the space if and only if any vector in the space is a linear combination of that set of vectors, a sum of multiples of those vectors. So, similar to what we did here, the typical vector in R3, I'll use ABC. Since we used AB for typical vector in R2, we'll use ABC. If we get too many, if the column gets too long, we probably go to subscripts. We run out of alphabet, x1, x2, up through xn, whatever n happens to be. But here, we can go ahead and use ABC. And since a lot of our work is going to be in R3, that's perfectly okay. Okay, there's your typical vector in R3. Here is a typical sum of multiples of the vectors v1, v2, v3. A linear combination of the vectors v1, v2, v3. C1's the number we multiply by v1, multiply C2 by v2, C3 by v3, add them up. That's a linear combination. So if we run through the whole process, we would write out the details of what this linear combination means. We would write out the simultaneous equations, and we would finally come up with a matrix equation, something like this. Okay, except we'd have a C3 here, you'd have a bigger matrix here, and you'd have an ABC here. The matrix that you would get would be 1, 0, 0, 1, 0, 1, 1, 1, 1. And again, the vectors V0, V2, V1, V2, and V3 would appear as the columns. Now you don't just memorize that the vectors appear as the columns. That's not even always going to be the case. You don't want to get used to the fact that your vectors are going to be in your columns. You want to see why the vectors are in the columns, so you work through all these details as we have in the past. Okay, and you think them through. Okay, if you get used to this process, maybe you are used to this process already, but you think, here is the condition, and this condition translates, let's see, we add these multiples, we're going to get the matrix, okay, we're going to get this matrix, and so forth. We're going to get these simultaneous equations. It's going to give us a matrix equation. And when I wrote this matrix equation, I left something out, something kind of important. Because clearly we never get that matrix. You're going to get C1 plus C2 plus C3 equals A, and then so forth, and so forth. 0 plus C2. So I wrote down the right things. I didn't write down the plus signs. In any case, this is the matrix we get when we write this out and add up the three vectors. And that then gives us the matrix equation that I have here. Right here is our matrix with the vectors in the column, and we see in the details why that works. Again, make sure you understand how to get from here to here. Don't just write this down. Okay, well, in any case, this then is solvable if and only if the determinant of this matrix is not 0, because this matrix can be reduced to the identity, giving us an inverse. This matrix can be inverted, etc., as long as the determinant is not 0, if and only if the determinant is non-zero. Okay, so, well, the determinant of this, and I simply observe when I look at this, if I want to calculate this determinant, I could multiply it all out, expand it by minors, do whatever, but I didn't bother to do that because I see that by switching these two rows, I would change the sign of my determinant to become the negative of the determinant I get when the two rows are switched. This being an upper diagonal matrix, the determinant is just the multiple of the diagonal elements, which are all 1, and we have the negative of that, so the determinant is -1. So clearly the determinant is not 0. It follows then that C1, C2, C3, the coefficients you would need to form a linear combination equal to the ABC vector, is equal to the inverse of this matrix multiplied by the ABC vector. Therefore, for any ABC vector, any vector in R3, we can multiply by that inverse matrix and get the constants that have the property that first constant times V1 plus second constant times V2 plus third constant times V3 equals the column vector ABC.